Hi, everybody, and welcome back. Today, we are going to be taking a look at our next section from Unit 4, and our topic for today is called integration by substitution. So when we first learned derivatives, everything was very basic. We looked at how you take the derivative of x to the n power, sine of x, cosine of x, natural log of x, e to the x. We did all the basic rules where it was basically just one type of function. Then we elevated that to incorporating the chain rule. Remember, the chain rule we used whenever we had one kind of function composed inside of another. So, for example, sine squared is a trig function composed inside of a quadratic function. So in that case, we have to use both rules. That's what the chain rule says. So we did all of our basic derivative rules. Then we learned how to take the derivative with something inside, and that was our chain rule. Now we are essentially going to do the same thing, but in the integration world. So we've learned all the basic integration rules. So we know how to take the integral of x to the n power, integral of sine of x, e to the x, 1 over x dx. All those are the basic versions of the integral. So again, essentially they are the results of taking the derivative of a basic function. But now we have to be able to take the integral of the result of a chain rule derivative problem. So when we did that with derivatives, we used something called u-substitution. So that's going to pop back up here. So the focus for today is we're going to be integrating composite functions. So again, a composite function is made up of several parts. Each thing's contributing to that function of change, the derivative. So when we integrate these derivatives, in order to find the original function that we started with, or the antiderivative, we have to make sure that all of the parts of the derivative are actually present before we can actually integrate. So it's a very similar process to the chain rule. The only real difference is when we did it with the derivative, we didn't have to make sure everything was present because we were starting with the original function. So we kind of created all of the parts. But when we integrate, we have to make sure that we have all the right constants or coefficients in the problem before we're allowed to go back. So there's just going to be a little bit of like fixing the integral so that we have what we need inside so that we can go backwards. So it's a pretty straightforward process once you get good at identifying all the different pieces inside the integral. So that'll be the toughest part to start with. Now, before we dive into the integrals, let's just go back and refresh. So this is the chain rule by definition. So if I were taking the derivative of f composed with g of x, then its derivative is f prime of g of x still. Remember, that was one of the big things with chain rule is that if you start with something inside, you always end up with that thing inside in the derivative still. That inside part, we can never just get rid of what the u is. It always showed up in that final result. But then we also have to multiply by the derivative of the inside. So that's our g prime. So if we just kind of flip everything back around, if this is the result, then I'm just going to integrate that result. And again, I have to have that dx quantity in there. But then we just revert right back to the original function that we started with. But then remember, we can always possibly have that constant of integration, that plus c guy, when it's indefinite integration. So for this unit, we're actually going to, or this section, we're actually going to go back to just plain old indefinite integration first to start, to make sure that you guys can, excuse me, handle the anti-differentiation part first. Then we'll mix in the fundamental theorem and do some definite integrals towards the end of the video, towards the end of the section. So now, when starting off with the integrals, it looks like a mess. There's a lot of different pieces in there. So just like with derivatives, we would always take the complicated stuff out, put something simple like u in, do all the math with the simple stuff, and then we put the complicated stuff back in. That's exactly what we're going to do for integration. So we're going to let u equal our inside function. So that part's not new. U was always the inside for derivatives, still is. But instead of using the u prime notation, we're going to use the differential equation that we see inside of our integrals. So think of dx. So instead of writing x prime, we write dx. So that's why we're going to stick with du notation. So I need to identify my u and then my du. So if u really is some function of x, in this case, we're just going to call it g of x, then rather than kind of looking for what's there, we just take the derivative of whatever this guy is. So what we get here, this result for du, is what we have to make sure is present inside of the integral before we can rewrite and do the problem. So if everything is there, then this g prime dx part, that is going to get replaced with du. Then we can integrate back just like normal. So the integral of lowercase f of u would become capital F of u plus c, and then again at the end, we just stick our u stuff back in there. So that's it. That's the whole process. So once we try a couple of these, you guys are going to get pretty good. And again, it's because we've already seen how the chain rule works for derivatives, and this is just kind of reverse engineering that process. So you should feel pretty comfortable with this rather quickly. It'll go a lot faster and a lot smoother than it did for derivatives because we have that familiarity already. So let's go ahead and try some of these. So when we do these problems, just like with chain rule problems, I always had you guys write down u and u prime. We're going to write similar information down. So we want to gather all the pieces, make sure we've got everything we need, and then we will rewrite, integrate, and then rewrite again. So for this first one here, I have the integral of 2x times the quantity x squared plus 1 squared dx. So again, just like with derivatives, we're looking for functions with an inside, something inside. So instead of x squared, we're looking for something squared, which is what we have here. So because this is a something squared, this guy that's inside of here, that's going to be my function. So, or excuse me, my inside function. So my u is going to be x squared plus 1. Sorry about that. I had to switch platforms real quick, but let's pick up. So if I have my inside function u is equal to x squared plus 1. So u is now a function of x. That's what we've just established here. The value of u depends on the value of x. So if I want to take the derivative of u, then it would have to be with respect to x because x is the input. So technically what I get is the quantity du dx. So again, think of like instead of y equals x squared plus 1 and getting dy dx, u equals x squared plus 1, so we get du dx. So if I write that out and then I take the derivative of this guy, derivative of x squared is just 2x. However, I don't have a du dx quantity inside of this integral. What I do have is a dx quantity. So what we do is we take this notation and we separate and move the dx quantity over to the right side. So instead of writing it this way, I'm always just going to simply write it as the du quantity is automatically going to be by itself because every one of these problems when I do this, I would want to move the dx back over to the right side with the other x stuff. So it ends up just tagging along and being multiplied by at the very end. So every problem for the du part, that's what it would look like, and that's how we would want to set this up. So because of that, now I have a u and a du, which is what I want. I want to be able to rewrite the integral in terms of u and du. And now if I go back and look at the structure of the problem, my u, so u equals x squared plus 1, is right here. So that's just the inside of those parentheses. Then I would need a 2x and a dx somewhere. Well, there is a 2x right here and a dx right here. The only thing that is not accounted for in u and du is the outside function. So whatever the outside function is, that should be the only thing that remains when I rewrite this integral in terms of u. So essentially, I'm taking it from a problem that is using two derivative rules, and I'm only going to focus on the outside one, just like we did with the derivative chain rule. So now I can rewrite this guy. So what I'm going to end up with is, this is equivalent to the integral of, again, if I replace x squared with x squared plus 1 with u, this becomes u squared. And then 2x and dx, both of those come out, and du takes their place. So we end up with the integral u squared du. Again, very simple integral now. All we see remaining is the outside function. If you were to evaluate x squared plus 1 quantity squared, the squaring is the very last thing that I would do in order of operations, so that's why that's the outside function. But now this guy is so easy because now I just use my basic integration rules just with the u variable. So the integral of u to the second power would be u cubed over 3 plus c. But now at the very end, we rewrite it again. So we rewrote it to make the calculus easier. Once we're done with the calculus, then we put the hard stuff back in there. So this ends up being x squared plus 1 quantity cubed over 3 plus c. That is the integral of, or the antiderivative of 2x times x squared plus 1 squared. Now, if you ever don't trust yourself, remember that this is a back and forth process. Just like if you multiply two numbers and you're not sure, you can take the answer divided by one of the factors and see if you get the other factor. There's always a way to check yourself. If I gave you the equation y equals x squared plus 1 quantity cubed over 3 plus 5, and I asked you for dy dx, you would set this up as a chain rule problem. My inside u would be x squared plus 1, u prime is 2x. When I rewrite it, I end up with u cubed over 3 plus 5. So its derivative, when I break the 3 down, they cancel. So we're left with u squared times u prime. Constant drops out. And in this case, that u prime is that 2x. So we end up with 2x times x squared plus 1 quantity squared, which is the exact thing that I started with inside of this integral. The only thing that's missing is that dx. And again, that guy comes from us moving that dx quantity over with all of the x variables. So this really is almost working in tandem, the same process, just in reverse order as when we took derivatives by the chain rule. All right, so let's try another one. Now I have 5e to the 5x. So again, you're always going to want to look for those natural insides. So things that have a normal spot where x goes, but now we've replaced it with something else. So remember, for exponential functions, x is normally in the exponent spot, but this isn't just x, this is 5x. So my u would be 5x. Again, we could write it as du dx and then every time multiply and move the dx over, but because we know it's always going to need to be on the right side, we can skip having to write that step out every time and just have it over there already. So the derivative of 5x is 5, and then I need the dx. So now when I go to rewrite, again, highlighting definitely helps visualize this, but we don't have to do it every time. Okay, so where I see 5x, that's going to get replaced with u. Where I see 5 dx, all of that is going to get replaced with du. And there should always be one thing that was not highlighted. That one thing is the outside function. So in this case, our outside function is that e function. So we end up with e to the u du. Integral of e to the u du is e to the u plus c, or e to the 5x plus c. And again, after a few of these, you guys are going to start really noticing the structure of these. And when you look at those final answers, you're really going to be saying to yourself, well, yeah, if I took the derivative of that, I would need e to the u times u prime. U prime is 5. So that's where they got the 5 from that's hanging out in front. Okay? All right, let's try another one. Now, there are some where the inside function is not as easy to recognize. So in those situations, you're going to have to be very creative, and sometimes it's just a matter of trying something. So for this next one, I have secant squared x times the quantity tangent x plus 3. So this one's a little bit harder. Now, there is a set of parentheses. So if you see parentheses, even if there is not necessarily a power attached on the outside, if there's a power attached, like the first one, then that's definitely our inside function. The inside parentheses would be inside of a power function. But in this case, there's no power on the outside of that group. So you may be wondering, well, what if that's not the inside? Well, one thing to keep in mind, somewhere inside of all these integrals is the derivative of the inside. One of these things, or sometimes several parts, in there have to represent your du, or the derivative of whatever we identify as u. So if you keep that mindset, sometimes you're going to notice that certain pieces inside look like the derivative of something else already. For example, in this case, I have a secant squared. The only time that we have ever worked with the function secant squared x in this class is either as part of the Pythagorean identities, which that's not what's going on here. Okay, we're not necessarily working with those right now. But more importantly, that is the derivative of the tangent function. And the fact that there is a tangent function inside of these parentheses should give you guys enough, like an alarm or an alert, that this is most likely the inside, and this guy is most likely a part of our du. So you do want to keep that kind of stuff in mind. We are looking for the inside and the derivative of its inside. So we have to have all those pieces to do this. So worst case, try something. Identify something that you think is the u, and then if it's wrong, you're going to need stuff for du that can't possibly be made. For example, now again, I know I just told you that this is our inside, but let's say that you don't recognize that right away. Let's say that you accidentally identify the other part as your u. If I identify secant squared as my u, to take that derivative, I actually need a chain rule. Now, while that is possible to do with these, it's very unlikely that your u requires a chain rule to come up with du, okay? The only time that would be the case is when we have one of those double chain rule problems. So it is possible, it's just not all that likely. But let's say that that is the case, and I wanted to try and do that. To take the derivative of secant squared, that would mean that secant is on the inside, and this guy is really v squared, and the derivative of v squared is 2v times v prime. The derivative of secant x is secant x tangent x. So my du would be 2 times secant squared x, or excuse me, secant x. So that's the v, and then times secant x tangent x. So really, if my u was secant squared x, then somewhere else, another factor of that problem would have to be 2 times secant squared x times tangent x. Well, I don't have another secant squared x anywhere in this problem. There is a tangent, but it's not a standalone factor. There's a term attached to that guy inside of these parentheses. So that's one nice part about this process, is if you try something and the thing you tried was wrong, you're usually able to catch yourself. Yeah, it's a little annoying that we have to erase and go back and try something else. But the good news is if your goal is to get it right and not just get it done, then it's nice having that kind of safety net to catch you. So always keep that in mind. Sometimes you're just going to have to try something, see if it works. If it fails, learn from it, move on, try something new. So the only other option is everything inside of this group then. So let's try using tangent x plus 3 as our u function. If I do that, the derivative of tangent is secant squared. Again, like we said earlier, derivative of 3 is 0. So we have the pieces that we need. So again, if I do the highlighting thing, we'll try this one more time and then without it the rest of the time. So if my inside here is my u, and then secant squared, oops, forgot my dx. It's an easy mistake to make, just be careful. But if I have secant squared x and then dx, so in this case, it looks like everything has been highlighted. So if that's the case, go ahead and rewrite it as you would. So this would become tangent x plus 3 comes out, u goes in its place. Secant squared x dx comes out, du goes in its place. So the reason why there was nothing left over that wasn't highlighted is because this is a power rule problem where the existing power is just 1. So technically speaking, there is a power on the outside of those parentheses. It's just 1, so it wasn't necessary to write it. So this is still power rule. Integral of u to the first is u squared over 2 plus c, or the quantity tangent x plus 3 all squared over 2 plus c. And that's it. Okay, let's try one more here before they get real tricky. So next one, we have the integral of 5 cosine of 5x dx. Another case here where it's pretty clear what the inside is. Remember that trig functions, exponentials, logarithms, radicals, those guys all have natural insides. So the most logical choice here would be that my inside is 5x because its derivative is 5 dx, and both of those pieces are here. So because I have what I need, I can rewrite this as 5x comes out, u goes in, which means the cosine function is still there. That's my outside function. 5x was composed inside of that in the argument. And then 5 dx comes out, du goes in its place. So we have what we need. The integral of cosine of u is just sine of u plus c. So we get sine of 5x plus c. And that is our final answer. All right, now we're going to take a look at problems where when we identify our u and our du, we're actually going to have something missing. So that happens sometimes where constants are just divided away, or they're not there to begin with, or they're there, but when we take the derivatives, they cancel out with other constant multiples that were already there in the first place. So for each of these, our approach is going to be the same thing. We're going to figure out what's the best candidate for our inside function, test to see if I take the derivative of that, do I have what I need, or do I have most of what I need? Or in other words, could I create what I need? So one rule for integrals that's really important, remember that the integral of 3x dx is the same thing as 3 times the integral of just x dx. So that is true whether it's an indefinite integral or a definite integral. That's one of the properties of these integrals. So basically what that rule means is if I have a constant multiple or a coefficient inside to start, I always have the ability to move it out in front. Why that's helpful is sometimes we either are going to have a coefficient that's missing, or we're going to have a coefficient that's not the right value. We need something else in there to match what our u and du would have to be. So because of that, we're going to be able to manipulate or kind of use this property to our advantage. And you'll see what I mean here in a second. Okay, so let's try this first one. I've got the integral of x times x squared plus 1 quantity squared dx. So that looks an awful lot like the very first one that we did a few minutes ago, this guy. So in this case, the only difference is that 2 that was in front. Now I needed that 2 because if u is the inside, x squared plus 1, then its derivative has to be 2x. So what that means is I'm not allowed to go from this form to in terms of u until I have everything exactly as it's labeled here inside the integral. Because if you think about it, I wouldn't be able to do my highlighting process that I did for a few of these if that 2 was not there. So this is what I mean by fixing it. So what we're going to have to do is I have to have that 2 in there. So if I have to have it, we're going to multiply this inside by 2 so that we have what we need. But I can't just go around doubling functions willy-nilly. You're not allowed to just create new numbers. But what you are allowed to do is multiply by 1. The only number that you can multiply by and not change the value of whatever it is you're multiplying by is 1. But we're going to multiply by a special form of 1, because any number divided by itself is equal to 1, which also means any number multiplied by its reciprocal is equal to 1. So what we're allowed to do is take any number that we need to have inside the integral, multiply by it inside so that we can identify our u and du, but then we just simply multiply by its reciprocal outside of the integral. And we're going to keep it there until the very end. Okay, so let's go through here. So again, if I want my inside again to be x squared plus 1, then its derivative has to be 2x dx. So again, if I go through and do all the highlighting stuff like we did in the for the first example, well, we have x squared plus 1, that's the inside. But then when I go to do my du, well, I need a 2x dx, but in the original form, there was only x dx. That's why we have to multiply by that 2. So we have to multiply by 2 inside, which means I have to multiply 1/2 out in front. But notice I'm not highlighting the 1/2 because that is not going to get replaced with the u stuff. That is there so that we can have a balanced integral, because I can't just multiply inside. Whatever we multiply by inside, we have to divide by or multiply by the reciprocal out in front. Now this rule only works with multiplication and division. You cannot add terms inside and subtract them outside. That's not okay. Okay? That's not the same thing. Remember, all of these integrals are based in the concept of area, which is multiplying 2 dimensions together. So we can't add something to area and subtract from it and have it be the same thing. It's not going to work the same way. Another reason why is because whatever we change, it's always going to have this factor of dx. And if I add a term inside, if I add something here, it's not going to have that dx quantity. And I can't subtract by something with dx outside of the integral. That dx really only exists inside of that integral. So that's the rule. We can multiply inside and multiply by the reciprocal out in front. So what that allows us to do now is now I'm ready to rewrite. So now this becomes 1/2 times the integral of u squared du. And then we integrate like normal, but at the end, you're going to have these extra coefficients out in front. So 1/2 times u cubed over 3 plus c. U gets replaced, so we have x squared plus 1 cubed. And then we just simplify the coefficients. 1/2 times 1/3 really is 1/6. And then we still have plus c. Which in the grand scheme of things, if you really think about it, the original problem was basically half of the original one, the one that we watched or tried the first time around. So that's where this 1/2 is out in front. And that's why the end result, this function, is exactly 1/2 of what the original was. So that's our idea, okay? Now, one thing here. So technically speaking, when we have this 1/2 out in front, I really should have put brackets around here. The only reason I don't is because when I have this plus c, some people want to harp on, well, that technically means the 1/2 has to be sent to here and to that c. So why don't we write it as 1/2 times c? Well, that's because c just represents any possible constant value. The idea is, remember that this represents a family of antiderivatives. So what the exact value of c needs to be is really dependent upon an initial condition. And if I don't have one of those, it doesn't really matter what this value of c is. That's why we just use the placeholder. But if c is any constant value, half of any constant value is some other constant value. So we don't need to really stress too much about having to multiply these constants by these extra coefficients. So this guy is really just always going to be some constant value, no matter what the extra coefficients are out in front. So essentially, let's do all the math, do all the calculus, and then that plus c is just going to go on at the very end, okay? All right, now, this next one, rather than there being a coefficient missing, we just have the wrong one, okay? Now, this one's a little bit trickier because we actually have two insides. This really only shows up with two kinds of functions. The secant-tangent derivative rule. Remember, secant-tangent is the derivative of secant. And then the same thing happens with cosecant. Derivative of cosecant is a negative cosecant of u and tangent of u, or excuse me, cotangent of u. So for those two, because the derivative of one function turns into the product of two, sometimes when we have this chain rule problem, we see that u thing show up twice. But it still kind of operates the same way. The most logical choice for an inside function is inside of these two. So that would be 4 theta. So if I had 4 theta as my u, du would be 4 times d theta. So essentially, I have the d theta that I would need. So let's highlight here. So we've got our u, and again, it shows up twice. But then for my du, I need a 4 times d theta. Well, right now there's a 7 out there. I do have the d theta that I need, but that 7 is not what I want inside. So what we have to do, similar to the first one, but I have to do something first. Whenever you have a coefficient inside already, and it does not match up with the number that we need, again, we can use this property and just move that 7 out in front. Once it's gone, then you can multiply by anything that you need or want to inside, and then balance it on the outside. So I need a 4 in here, so I'm going to multiply by 4 inside of the integral, which means I have to divide by 4 out in front. So if we had already moved the number out in front, and then we have to do something to balance it, then those two numbers just interact like they would with any multiplication. So 7 times 1/4 is just 7 over 4. So now I am ready to rewrite this. This becomes 7/4 times the integral of secant of u, tangent of u, du. Integration of secant of u, tangent of u, that just turns into secant of u plus c. And then again at the end, we can substitute our u back in there. So we get 7 over 4 times secant of 4 theta plus c. And again, whenever you guys get to results for these u-substitution problems, if you're unsure of your answer, if it looks weird and you don't think you did it correctly, do some mental math. You can always write it down if you want to, but if you do some mental math and try to do it in the derivative order, you should work out back to what you started with. This is a 7/4 times secant u problem. My inside's derivative is just 4, so when I multiply by that, it's going to cancel. That's how I got the 7 that was out there to start. And then the derivative of secant is secant tangent. So that's where we get secant 4 theta, tangent of 4 theta. So again, you can write stuff down if you need to, but we've done these derivative problems long enough, and you guys should have enough experience now that it shouldn't take you too long to do some mental math checking them. All right, let's run through some of these. So each one of these is just a different variation of looking for that inside and checking to see, do I have to fix something? Not all of these require us to fix something, but some of them do. All right, so for the next one, I've got negative 5x over the quantity 1 minus 2x squared, quantity squared dx. So again, natural insides, parentheses with powers on the outside makes the most sense. 1 minus 2x squared, that derivative would be negative 4x dx. Now, with fractions, sometimes people get confused about like what's being multiplied by the dx quantity and stuff. Well, again, just think of this as just regular old numbers, okay? Something divided by something multiplied by something. Well, remember this guy that's just floating out here to the side, I could really put it over 1 and multiply it with the numerator. So that dx quantity can move. It can be out on its own at the very end like it is right now, or we could technically move it into the numerator with whatever's going on up there. So if I did that, I have almost what I need. I want it to be negative 4x dx, but it's negative 5 dx right now. So easy fix. I'm going to move the 5 out in front. I don't need to move negative 5 out because I want the inside to be negative. So right now it's negative 1x dx. So I'm going to multiply by 4 inside, which requires me to divide by 4 outside to balance. So now when I go to rewrite, I end up with 5/4 times the integral of 4x dx, or excuse me, negative 4x dx. All of that is du up top. And then on bottom, I have u squared. Now, if you go back and look at your derivative or integration rules, there's no rule for du over u squared. But that's because this is a power rule that's hiding with a negative power. So we can rewrite this one more time and make this u to the negative second du. Now, some of you may want to jump straight to this step and skip over this middle guy. That's perfectly fine. That just means that you're a little bit more advanced and you're recognizing that structure, and that's a really good thing. All right, now we do our calculus. Again, we haven't done any calculus up to this point. So adding 1 gives me u to the negative first, divided by negative 1, and divided by that new power, and then plus c. So really, dividing by negative 1 just makes this whole thing negative. We don't typically like the negative sign in the bottom of a fraction, so I'm going to move it up top. 5 divided by negative 1 is still just negative 5. But then u to the negative first, that guy needs to go down in the bottom. So this is going to become 4 times my u to the first power, or just 1 minus 2x squared plus c. So we could leave it like that. You really could distribute the 4 inside if you wanted to. Just for the sake of space, I'm going to skip over that. That part's not super crazy. All right, next one. Now this one's a fun one. So this, excuse me, this one doesn't have like a natural inside because there's 2 sets of parentheses here. You can't have both things being the inside function. But what that does mean is that one of these is our u and the other one is our du. There's no other way to mix and match it. So one is u, one is du. So worst case, try one and see if it makes the other. If you don't get it right the first time, just flip-flop it. Try it the other way. Now, I'm not going to write it down twice because I'm pretty good at calculus, so I don't need to. I can look at this and tell, well, I know the derivative of e to the x is e to the x, and I know the derivative of x is 1. So this first group has to be my u. So e to the x plus x would be u, then that makes e to the x plus 1, and this is the first one we've seen where u is multiple terms, and the derivative is still multiple terms, so we need parentheses around it, and then that dx quantity. So we have exactly what we need here for du. This one does not require us to rewrite it. This one, I can jump right to substituting it, and it becomes u du, or remember that is u to the first power. So then integral of u to the first would be u squared over 2 plus c, or in this case, we get e to the x plus x, quantity squared over 2, plus c. All right, our next one, this one's, it looks pretty scary. But again, the hardest part, or really the most important part, is figuring out that inside. Once you get that part going, it will make the rest of it a lot easier, okay? So that's always step one. So for this one, if you notice, we've got a big radical in the bottom. So the fact that it's in the bottom means it's really a fraction exponent on a group, but it's a negative fractional exponent on that group. So keep that in mind as we do this. But seeing that radical and the fact that it's not just the fifth root of x means that inside has to be my u. There's no other way around this one. So my u automatically has to be 6 plus natural log of x. If that's the case, then du would be, don't need parentheses here. 6, that derivative just goes away, but natural log of x, that is 1 over x dx. So what that really means is, again, my dx is taken care of. That guy is over here. So I need 1 over x dx. dx is okay. The 1 over x means that the x, there needs to be an extra factor of x somewhere in the denominator. And that's why this guy is hanging out here. Okay? Now, for my inside, I can go ahead and do that one. So one thing, and I don't think I said this earlier in the video, when we fix these guys, it's always because stuff is missing for du. You will never have to do anything to fix the u. We set up what u is, and that's how the process starts. So it's not like we ever have to multiply inside and out to make u be what we need it to be. It's always fixing du. But the issue here is we have two things that aren't highlighted, the fifth root and that 4. Well, remember, all that means is that 4 is an extra factor or an extra coefficient. So I'm just going to move him out in front, out of the way. So now it's just 1 up top. That matches what I have in the du. The fifth root part, though, that is my outside function. So when I go to rewrite this, I end up with 4 times the integral of, and I can really write this as, and actually, I want to overcomplicate things, 1 over u to the 1/5 power, and then du off to the side. So what I was about to do was write du in the numerator. And again, technically I can. I just don't want to confuse anybody doing that. So again, this isn't the best form. This is going to be a power rule. But remember, I need it written as u to the n power. So we're going to bring this up now. And this is where that negative exponent comes into play. So it's really u to the negative 1/5 that I'm going to integrate. So when I do that, remember I still have 4 out in front. So I'm going to have 4 times add 1 becomes 4/5 for the new power, but then remember we divide by that power. So we're going to divide by 4/5. But oops, sorry, not du, plus c. But remember that when we do that, when we're dividing by that new power, if it's a fraction, we are actually going to end up multiplying by its reciprocal. So the 4's cancel, and so we end up with 5 times 6 plus natural log of x raised to the 4/5 power plus c. So this is where you can kind of see the structure again of where some of the parts of the original problem came from. So if I were doing this as a derivative problem, the old power comes down in front, and 5 times 4/5, the 5's cancel, and that's what leaves that 4 in that numerator. That's where these weird numbers can come from. It's because the coefficients that were in the original, something ends up canceling out, and the part that's left behind is not something that we would have expected to see. Okay. All right, let's try another trig one. So this one's a little tricky. It's the integral of 3 cosine squared x sine of x dx. So this one, we're going to try a couple things just to see if they work out. So most people, most students, when they see this, their first instinct is just going to be, well, either this guy is my u or that guy's my u. So let's just try each of those and see what happens. Now this 3, again, that is the case where we really just have an extra thing. So that extra coefficient, we're just going to move it out of the way and not have to worry about it, okay? Looking at these other pieces, there's no logical reason to expect a 3 to show up or be needed as part of our derivative. There's no other numbers in there, so it's not like something we need to be concerned about. That's why it's okay to move it out. So let's start with the first one. Let's say that I think cosine squared x is my u. Well, to take the derivative of that, this is something squared, so this is where I would need a v. So if I think of this as v squared, where v is cosine, then v prime would be negative sine of x dx. So v squared would turn into 2v times v prime, or negative 2 sine of x cosine of x dx. Well, I don't have all of that stuff in there. The only other thing I have is a sine. You are not allowed to multiply by functions of x inside and outside. The only thing that we can do to change these is multiply by numbers inside, multiply by numbers outside. So it's not as simple as just multiplying by the extra functions that we need. So this setup does not work. So if it doesn't work with cosine squared being our u, then if we reset, let's try the other piece. So if u is sine of x, then du would be cosine of x dx. And that looks like it's a little bit more promising, but the issue there becomes I do have a cosine, but this is cosine squared, which really means cosine times cosine. So that would leave out an extra factor of a function of x. So again, it would be okay if the only thing left over was a constant, a constant multiple, excuse me, that we can move outside. We can't move that extra function of cosine x outside. Otherwise, we wouldn't be able to finish this problem. So if the two obvious choices don't work, then we have to think of unconventional things. We have to kind of think outside the box. So this is a particular kind of common problem, and it typically will show up with trig. This is an example of a double chain rule. So this is not a double chain rule. This is one of those problems where the trig function was raised to a power. So this is particularly difficult to recognize when we do integration. With derivatives, it was a little bit easier to recognize because it would just be sine raised to a power or cosine raised to a power to start. But now you see two trig functions next to each other, so it's a little bit more difficult. So now what we have to do, our inside function is actually inside of this squared function. Remember that cosine squared can really be rewritten as that guy. So if the whole thing looked like this, then it would be a little bit easier for us to recognize the inside, because now it's clear cosine is inside of the squared function. So you have to be very careful, be on the lookout for trig functions raised to power, specifically sines and cosines. This typically happens a lot when sines and cosines are raised to powers. It can happen with other ones, but remember that secant and cosecant, they're actually derivative rules raised to powers. Remember, derivative of tangent is secant squared, so that one can show up in other ways, okay? But in this case, if I tried to let u be cosine of x, not squared, just regular cosine, then for du, I would need negative sine of x dx. So now if I tried to go through and do my highlighting routine here, u would be cosine, and actually let's use this form. So I can highlight cosine right here. Then for my du, I need a negative sine of x dx, so I need three pieces. Well, I have the sine of x dx right here, but I still need a negative. So we need to multiply by negative 1 out in front. Whoops, I don't want to highlight that. So I need to multiply by negative 1 in front, which means, and we still have this 3 hanging out in front. So if I multiply by negative 1 in front, again, technically I would divide by negative 1 to counteract, but when it's just a negative sign that we need, we can essentially just multiply by negative 1 inside and outside because those cancel each other out. So rather than writing divide by negative 1, it's just easier just to put that negative sign out in front. Because now if I were to bring all of this stuff back in, it takes me right back to where I started with a positive 3 coefficient. So because of that, now I have everything that I need. Now I have my negative inside. So now I can rewrite. This would give us negative 3 times the integral of u squared du, or negative 3 times u cubed over 3 plus c. That means these 3's cancel, and I am simply left with the opposite of, actually you could write this as a parentheses cubed, but with the trig functions, when we write, oops, still not getting it right. When we write our trig functions raised to powers, we typically will use this shorthand notation. So this would be the opposite of cosine cubed x plus c. And just in case anybody was wondering if that negative that we multiply by out in front affects the plus c, we will always write plus c because, again, it represents any constant, including negatives. So if we solved for c and ended up being negative, then we would just write minus that number. So we don't have to account for that or change anything with our plus c notation. All right, let's try another trig problem. This was the one that I was thinking of. So we could go through the same routine that we just did. Let's try sine squared of blah, 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 cosine of blah, blah, blah. But now that we've seen one like that, it should be a little bit more obvious to us what's going on here. So with that in mind, let's try and approach this the same way. So if I were to think of this as sine of x over 3 quantity squared, that makes it a little bit more obvious to us in this case that that sine function is inside of the squared. So because it's inside of the squared, that's going to be my u. But the problem with this is now to take that derivative, I actually need a chain rule for derivatives. This one is an example of a double chain rule. So when the double chain rule problems pop up, we have to account for all of that extra differentiation. So to do that, we're actually going to do it just like we did with the derivative problems. Well, the inside of this guy, v, is x over 3. So this is really sine of v. And the derivative of sine of v is cosine of v times v prime, where v prime is 1/3. So my du, what I actually need to make sure that I have here is 1/3 cosine of x over 3. So now if I go through here and do my highlighting trick, again, this isn't something you guys always have to do, but I definitely think it helps. So I have sine of x over 3, that's my inside function. Okay, that's my u. Then for du, I need a 1/3 cosine of x over 3. So, oops, I forgot my dx again. Again, it's really easy to forget that. You guys got to be careful. Okay. So the cosine x over 3 dx part is all good, but now you see I'm missing a 1/3. So this is another situation where we're going to multiply inside by the fraction 1/3. So on the outside, I multiply by its reciprocal or divide. So in this case, this would just turn into a 3 out in front. So if I multiply by a fraction inside less than 1, we end up multiplying by a bigger number outside. So I have everything that I need. Now I can rewrite this. This is 3 times the integral of u squared du. So then let me jump down here. Integral of u squared, this would be 3 times u cubed over 3 plus c. And in this case, the 3's just cancel each other out. And then we end up with sine cubed of x over 3 plus c. So again, if I go backwards and I think about or try to do this derivative mentally, I start with sine cubed of something. So its derivative, bring down the old power, 3 times sine to the new power squared of the old argument, x over 3, times the derivative of the inside. Well, the derivative of sine is cosine of x over 3, but then the derivative of x over 3 is 1/3. That's why the 3 and the 1/3 cancel. That's why there was no coefficient in the original. So we're just left with the sine squared of x over 3 times cosine of x over 3. All right, one more. For this one, so we just did a couple of these trig problems, so some of you guys may think, oh, well, let's make the inside it. This one is actually neat. There are 2 ways to solve this problem, and we get equivalent answers. Not going to be identical, but they're equivalent to each other. So let's try this. We'll do it both ways, and then you guys can see how they end up being basically the same thing. So one possible way here, again, if you kind of look at the 2 pieces, we basically have 2 factors. The logical choice here for u would be tangent of x, and that's because its derivative is the other factor here, secant squared x dx. So that's the easiest, most straightforward way to do this one. So if I set it up that way, when I go to rewrite, I have everything that I need. I don't actually have to fix anything here. So we just end up with u du. Remember, this will be a common one that you guys will come across, and a lot of times this one gets overlooked, or it can be tricky because it doesn't necessarily look like anything, but remember, u or x is just a power rule still. It's x to the first, or in this case, u to the first. So this will become u squared over 2 plus c, or in this case, tangent squared x over 2 plus c. And we could always move that 1/2 out in front. Some people don't like writing the fractions like that with the trig function, so we could always just write 1/2 tangent squared x plus c. All right, so that is one way to do this. Another way to do this is I can actually rewrite this original piece. So if I rewrite it, I can make this secant x times secant x tangent x dx. So it's not that this would be necessary to do, it's just another approach. So if I chose to do it that way, then now I could let my u be secant of x, and its derivative du would be secant x tangent x, which I have. And so now when I rewrite this, this becomes the integral of u to the first du again. So we end up getting u squared over 2 plus c for this, but now the u squared here is our secant x function. So we end up with secant squared x over 2 plus c. So we end up with our two different answers. They look different, but if you remember, tangent squared and secant squared are connected to each other through the Pythagorean identity. One of the alternate forms of sine squared plus cosine squared equals 1 is 1 plus tangent squared x equals secant squared x. Or in other words, the only difference between these two guys is some constant value. So essentially, all that means is for these two to be equivalent to one another, even with the 1/2 out in front, I really just need the right value of c. So if I did the problem this way and I had a particular solution, I would get one value of c. But if I do the problem with the same initial condition using the second setup, I would get an equivalent form. It would just be a different value for that constant. Or another way of demonstrating this is using Desmos. Here we have the graph in red of 1/2 tangent squared plus x. Let's add on a constant called c1 to that guy. And then down here, let's make our blue graph. Here is secant squared of x. Let's add a second constant on to there. So really, if c1 for tangent is 1, all I really need to do is adjust this constant to make it be something so that these guys actually match up. So I can't make it exact. Oh, actually, there we go, 0.5. So again, it's the difference is really just that constant value. And that's, again, ties back into the Pythagorean identity. And really, they're only separated by that +1 value. So what that tells us is there's going to be a variety of ways to solve some of these. The biggest and most important thing is just try something. Figure out what you think the u is, see what you would need for du, and then try it that way. If it fails, and then we go back and try something else. These problems aren't impossible. They're just going to take a little bit of work, and it might take several attempts to try and figure out what the right setup is. Now we're going to take a look at how we do this u-substitution in or using definite integration, so our fundamental theorem. So whether it's just here's a definite integral, evaluate it, or here's a function and an interval, find the area between the x-axis and that function on this interval, whatever the exact setup of the problem is, that part doesn't really matter. The idea is we need to be able to solve a definite integral when u-substitution is required. So for right now, what we're going to do is we're going to start the problem the same way we did before and kind of ignore the a and b values just for the get-go, or from the get-go. So the integral from 0 to 1 of x times x squared plus 1 quantity cubed dx. So I have a natural inside here. X squared plus 1 is the most logical choice because it's inside that group raised to a power. And if that was the case, then du would need to be 2x dx. So I need to fix this guy. I need a factor of 2 inside, which I don't have. So let's multiply by 2 inside and 1/2 outside to keep it balanced. So now, if I go and rewrite the problem right now, I would, and if I left it the way it is right now, I would end up with 1/2 times the integral from 0 to 1 of u cubed du, Well, the problem with that is when I continue this, if I start to take my antiderivative and stuff, the variables inside are u's, but our bounds of integration, our a and b values, those are x values. They were referring to the value of x equals 0 and 1 for this original function. So what we have to do is called something change of variables. Now, there's a couple different strategies for this. Some people like to do everything in u's and then turn back to x's once the calculus is done and then just use the original a and b's. And that has some merit. It's not a bad way to do it, but the issue is it becomes confusing when we write an integral like this where we're in terms of u, but our a and b values are really x values. It's not proper mechanics when we write these out. So instead of writing it that way, we're going to add 2 more levels to our setup information. So to start, we had x equals 0. That was our lower integration value. Well, if u is equal to x squared plus 1, we have a defined relationship that connects values of x to values of u. So what we do is just swap these out. If x equals 0 and I substitute this in here, I get u is equal to 1. So instead of 0 being my lower bound of integration, now it's going to be 1. Then we'll do the same thing for my b value. My b value was 1, and if u is equal to x squared plus 1, when x equals 1, u is equal to 2. So that becomes my upper bound of integration. And now that's why this is more proper. Everything in this problem is now in terms of u. And the best part about this is I don't ever have to go back to x's at all, because I've completely turned this problem into a problem that depends on the value of u. So if I don't do it this way, after you do your integration and you get your antiderivative, then you have to put all the x stuff back in there and then plug your original a and b values into that. So no matter what, substituting 0 and 1 into this function somewhere is going to occur at some point. We're just choosing to do it at the beginning because if I do it then, all of the stuff after the calculus is super easy. And you can see that when we finish this. So I would have 1/2 times the integral of u cubed is u to the 4th over 4. And now I'm going to go from 1 to 2. So again, the difference is I'm just not going to replace my x stuff back in there for u. We're going to leave it in terms of u. And I can do that again because my a and b are values of u now. So that would give me 2 goes in, 16 over 4 is 4, minus 1 goes in, 1/4. So this would give me 1/2 times 15/4, or 15/8. So that is my final answer. And all I had to do, the only extra thing, were these 2 lines. I had to replace the old AB values that were in terms of x, substitute them into my u equation to get u values at those x values, and then I just finished the problem out in terms of u. Again, if I chose not to do it that way, if I don't want to do this line, then after I get my antiderivative, then I have to turn this back into terms of x's. So I would have to write it as x squared plus 1 quantity to the 4th power divided by 4, going from 0 to 1. So from there, I would stick 1 in. So it would still be the exact same math that I did here. It's just you're going to have to do a little bit of extra stuff in there. So that's the benefit. We got rid of that extra step there by doing it at the beginning, so it makes it just a tad bit easier for us. So we end up with our 2 different answers. They look different, but if you remember, tangent squared and secant squared are connected to each other through the Pythagorean identity. One of the alternate forms of sine squared plus cosine squared equals 1 is 1 plus tangent squared x equals secant squared x. Or in other words, the only difference between these 2 guys is some constant value. So essentially, all that means is for these 2 to be equivalent to one another, even with the 1/2 out in front, I really just need the right value of c. So if I did the problem this way and I had a particular solution, I would get one value of c. But if I do the problem with the same initial condition using the second setup, I would get an equivalent form. It would just be a different value for that constant. Or another way of demonstrating this is using Desmos. Here we have the graph in red of 1/2 tangent squared plus x. Let's add on a constant called c1 to that guy. And then down here, let's make our blue graph. Here is secant squared of x. Let's add a second constant on to there. So really, if C1 for tangent is 1, all I really need to do is adjust this constant to make it be something so that these guys actually match up. So I can't make it exact. Oh, actually, there we go, 0.5. So again, it's the difference is really just that constant value. And that's, again, ties back into the Pythagorean identity. And really, they're only separated by that +1 value. So what that tells us is there's going to be a variety of ways to solve some of these. The biggest and most important thing is just try something. Figure out what you think the u is, see what you would need for du, and then try it that way. If it fails, and then we go back and try something else. These problems aren't impossible. They're just going to take a little bit of work, and it might take several attempts to try and figure out what the right setup is. Now we're going to take a look at how we do this u-substitution in or using definite integration, so our fundamental theorem. So whether it's just here's a definite integral, evaluate it, or here's a function and an interval, find the area between the x-axis and that function on this interval, whatever the exact setup of the problem is, that part doesn't really matter. The idea is we need to be able to solve a definite integral when u-substitution is required. So for right now, what we're going to do is we're going to start the problem the same way we did before and kind of ignore the a and b values just for the get-go, or from the get-go. So the integral from 0 to 1 of x times x squared plus 1 quantity cubed dx. So I have a natural inside here. X squared plus 1 is the most logical choice because it's inside that group raised to a power. And if that was the case, then du would need to be 2x dx. So I need to fix this guy. I need a factor of 2 inside, which I don't have. So let's multiply by 2 inside and 1/2 outside to keep it balanced. So now, if I go and rewrite the problem right now, I would, and if I left it the way it is right now, I would end up with 1/2 times the integral from 0 to 1 of u cubed du. Well, the problem with that is when I continue this, if I start to take my antiderivative and stuff, the variables inside are u's, but our bounds of integration, our a and b values, those are x values. They were referring to the value of x equals 0 and 1 for this original function. So what we have to do is called something change of variables. Now, there's a couple different strategies for this. Some people like to do everything in u's and then turn back to x's once the calculus is done and then just use the original a and b's. And that has some merit. It's not a bad way to do it, but the issue is it becomes confusing when we write an integral like this where we're in terms of u, but our a and b values are really x values. It's not proper mechanics when we write these out. So instead of writing it that way, we're going to add 2 more levels to our setup information. So to start, we had x equals 0. That was our lower integration value. Well, if u is equal to x squared plus 1, we have a defined relationship that connects values of x to values of u. So what we do is just swap these out. If x equals 0 and I substitute this in here, I get u is equal to 1. So instead of 0 being my lower bound of integration, now it's going to be 1. Then we'll do the same thing for my b value. My b value was 1, and if u is equal to x squared plus 1, when x equals 1, u is equal to 2. So that becomes my upper bound of integration. And now that's why this is more proper. Everything in this problem is now in terms of u. And the best part about this is I don't ever have to go back to x's at all, because I've completely turned this problem into a problem that depends on the value of u. So if I don't do it this way, after you do your integration and you get your antiderivative, then you have to put all the x stuff back in there and then plug your original a and b values into that. So no matter what, substituting 0 and 1 into this function somewhere is going to occur at some point. We're just choosing to do it at the beginning because if I do it then, all of the stuff after the calculus is super easy. And you can see that when we finish this. So I would have 1/2 times the integral of u cubed is u to the 4th over 4. And now I'm going to go from 1 to 2. So again, the difference is I'm just not going to replace my x stuff back in there for u. We're going to leave it in terms of u. And I can do that again because my a and b are values of u now. So that would give me 2 goes in, 16 over 4 is 4, minus 1 goes in, 1/4. So this would give me 1/2 times 15/4, or 15/8. So that is my final answer. And all I had to do, the only extra thing, were these two lines. I had to replace the old AB values that were in terms of x, substitute them into my u equation to get u values at those x values, and then I just finished the problem out in terms of u. Again, if I chose not to do it that way, if I don't want to do this line, then after I get my antiderivative, then I have to turn this back into terms of x's. So I would have to write it as x squared plus 1 quantity to the 4th power divided by 4, going from 0 to 1. So from there, I would stick 1 in. So it would still be the exact same math that I did here. It's just you're going to have to do a little bit of extra stuff in there. So that's the benefit. We got rid of that extra step there by doing it at the beginning, so it makes it just a tad bit easier for us. All right, let's take a look at this next one now. So same idea. We've got integral from 1 to 3 of e to the 3 over y power over y squared dy. So there's a lot going on in this one, but again, if you identify some of the kind of standout types of functions, groups raised to powers, radicals, exponential functions, logarithmic functions, trig functions, if one of those exists in your integral, each one of those comes with a natural inside. So in this case, we have an exponential function. That natural inside is the exponent location. So if I tried to let u equal 3 over y, or remember 3 over y is the same thing as 3 to the negative, or 3y to the negative first power, to take that derivative would require a power rule. So that would give me negative 3y to the negative second, or negative 3 over y squared. That is where, don't forget our dy, that's where this y squared in that denominator comes from. So the only thing missing from this du is a factor of negative 3 in the numerator. So we need to multiply by negative 3 up top, which means multiply by negative 1/3 outside of the integral. Now we're also going to go ahead and set up our new a and b values. So when x equals 1, according to our equation, u is equal to, or excuse me, not x. Sorry, this one is in terms of y to start, so we're going to change that. And we're going to make that y equals 1. So when y equals 1, u is equal to 3 divided by your y coordinate, so we get u equals 3. Then when y equals 3, u would be 3 divided by 3, so we get u equals 1. So when I go to rewrite this whole thing, now in terms of u, we end up with negative 1/3 times the integral from, now this is where this one gets a little weird. So this happens a lot of times when your u is some kind of ratio with a variable in the bottom. What ends up happening is because that variable is in the bottom, when I put small values of the old variable in, it makes a bigger new value. And when I put big values of the old in there, it makes a smaller new value. So what ends up happening here is the size of our a and b values just flip-flopped. So this is still a, this is still b. So when I rewrite this, I get the integral from 3 to 1 of e to the u du. So again, the negative 3 over y squared dy, all of that got replaced with du. And so I'm left with e just to my u power. So the issue here now is we don't like to integrate when our a and b values are backwards. Remember, it always has to go from a smaller value to a larger value. So one of the properties of integral says that we are allowed to flip-flop our a and b values as long as we change the sign of the integral. So I'm going to go ahead and do that. So instead of 3 to 1, we're going to make it correct and go 1 to 3. But now that changes the sign outside, out in front of the integral, to it, since it was negative 1/3 in front, now it will be positive 1/3. So now everything's fixed. Now we can continue and finish in terms of u. So again, I don't have to go back to any of the y stuff that we started with. So we just end up with 1/3 times the integral of e to the u is e to the u from 1 to 3. So I would get 1/3 of e cubed, minus e to the first. And those don't really simplify any better. So we could leave it like this. One alternative form of writing it would be to put all of that over 3. That's typically how most textbooks would write it, but both of these are really acceptable forms. There's not really any good way to simplify that answer. But again, hopefully you guys understand why we're doing this whole change of variables thing. That it avoids having to go back and do math after the calculus is done. And doing it ahead of time just kind of makes it an easier finish to these problems. Now, sometimes our basic u-substitution kinds of problems aren't going to work. So for example, this guy here, I have the integral of x times the square root of 2x minus 1 dx. So let's say that I tried to set this up like a normal problem. Now notice this one is indefinite, so I don't have to worry about change of variables. But let's say that I tried to set this up like a normal u-substitution problem. I have a radical. Radicals have a natural inside. So obvious, or the most obvious choice here, most logical choice, would be letting that inside be my u. So if u is equal to 2x minus 1, then my du would be 2 dx. So if I did go through and do my highlighted stuff, so my u is 2x minus 1, so that's inside of here. That's all good. And then for my du, I need a 2 and a dx. Well, I have the dx. I don't have the 2. So I can fix that, though. We know how to do that now. So I can multiply by 2 inside the integral, but that means I have to multiply by 1/2 out in front. So now I have what I need for my du, but the issue becomes we have something extra. So for this one, I did not want to highlight that, but that'll work. In this case, we have an extra factor of x. So if it was an extra coefficient, just a number, then remember we've seen problems like that earlier in the video. We could just move that guy out in front and not worry about it. You cannot move functions of x inside or outside of the integral. So if it's in there, we have to do something with it. We just can't move it outside. That would be easy, but we're not allowed to do that. So instead, what we have to do, anytime that you have extra factors of x, whether it's in the top or bottom, sometimes they'll show up in either, but anytime that we have extra functions of x that are not accounted for by a simple u and du setup, we have to actually consider what would x be equal to in this established relationship. Again, as soon as I write this first line, we're saying that there is a connection between the value of u and the value of x. So one way around this is to solve that relationship for x and use that to replace it in the original integral. For example, if I solved this equation for x, I would add 1 to both sides and divide everything by 2. So I would get u plus 1 all over 2. That is the same relationship that we established here, just in reverse order. But what that allows me to do is now I have accounted for everything that is in the original integral. Now I have something to replace that x with. So when I do this, it's going to be a little tricky. Let me get rid of red. I don't want to use that anymore. So I have the 1/2 out in front still. Now inside, 2 dx, all of that is taken care of. That's my du. Square root of 2x minus 1, that now becomes the square root of u, or I'm going to write that as u to the 1/2, because again, I know the power rule is coming. But then this x, that one little extra factor out in front, is equal to that whole group. So we are going to have to replace it with u plus 1 all over 2. So these are definitely more complicated. These are about as difficult as these chain rule problems can really get because of that extra little piece in there. But now all this does is it just creates a new problem for us, and we have to solve all of this in terms of u. At the very end, because this isn't a definite integral, we'll stick our x stuff back into that final result. So let's simplify this a little bit. So I have 1/2 times the integral. So what we have here really is just a polynomial, or a mixture of polynomials and these radical terms that we need to multiply together. So really, this is factor 1 times factor 2 times factor 3. Factor 1 has a fraction factor inside of it, so I'm going to pull that guy outside, and I'm going to move him out in front. Since there was already a 1/2 here, if I bring another 1/2 out there, it would become 1/4. So doing that's going to make this a good bit easier for us. So this guy's gone now because I turned this into 4, and now I'm just left having to distribute u to the 1/2 to both of these. So that gives me u to the 3/2 plus u to the 1/2 times du. That's much easier to work with than the form that we had when we first rewrote it. Now this just becomes two power rule problem, so nothing crazy difficult. So I'm going to get 1/4 times u to the 3/2. That antiderivative, we add 1, we would get u to the 5/2. Divided by 5/2 is like multiplying by its reciprocal, 2/5. Plus u to the 1/2, add 1, new power becomes u to the 3/2. Divided by 3/2 is like multiplying by its reciprocal, 2/3. Going to tack the plus c on there at the end. Let's distribute this 4 inside. So when I send 4 in, both of these numerators have a factor of 2. So let's go ahead and reduce those out, turn this guy into a 2. So it's really just going to be 1/2 now that I'm distributing inside. So that would give us u to the 5/2 over 10 plus u to the 3/2 over 6 plus c. Let me fix that 10. It looks like a really poorly written infinity. Here we go. That is it. So you just have to be on the lookout for these. So when you approach one of these problems, there's not a huge red flag thing in here that when you look at it at the start, you immediately can recognize that there's an issue. Really the only thing, if I go back and erase some of this stuff, if I was looking at this problem from the start, the only thing that is kind of a red flag to me is, again, my eyes get drawn to the radical immediately. And now I've been doing this a lot longer than most of you guys have, so you may not be quite at this level right at the start, but eventually you're going to get here. The derivative of this inside, I know this is a linear, so its derivative has to be a constant. So as soon as I see this extra thing outside, then I know that this is probably going to be one of these problems with something extra. Now, if I had the integral of x times the square root of 2x squared minus 1 dx, then I wouldn't be as concerned because now the inside is a quadratic and the derivative of a quadratic is a linear. And I know the constant would disappear. So this would be a case where I just need to fix the coefficient inside of the integral. So that's kind of really the only red flag thing that we can look out for. So these are problems where you may pick up on that right away, but if you don't, if you're going through the motions and setting up your u and your du and you have something left over, now you guys know how to attack it. All right, now, last problem in this section, it's a multi-step one. It's just an application problem, how we can use this u-substitution stuff in some of our other scenarios that we've talked about in the past. So for this one, it says, a particle is moving along the x-axis for all values of t greater than or equal to 0. It has an acceleration modeled by the function a of t equals 8 times 2t minus 1 quantity cubed. The particle has an initial velocity of v of 0 equals -3 and starts at the origin. So this last part is actually another way of giving the initial condition that x of 0, is equal to 0. So it's actually a second initial condition. Remember, we can use those. If I start with one function and I use indefinite integration, I can go backwards and use the initial condition value to find that c. So I could do this twice and make it all the way back to the position function. So that's why part A and B here, that's what you're asked to do, okay? So to find the velocity function, we are going to take a of t and integrate it, and then use our initial velocity here that's given to us to find that c value. So that's how we're going to start. So I'm going to integrate 8 times 2t minus 1 quantity cubed dt. So from the start, I would say u equals that inside, natural inside. Du then would need to be 2 dt. So this 8 does not match up with what I want it to be, so let's move it outside and then make what we want it to be. So I need to multiply by a factor of 2 inside, which really means I'm dividing by 2 outside. So again, if you move something out and then have to balance it still, we just, when we do that extra math out in front, they just interact together like regular coefficients would. So now we have everything we need. 2 dt is there. I've got my u to the 3rd power. So my result is 4 times the integral of u cubed du, or 4 times u to the 4th over 4 plus c. So the 4's here will cancel. So my general velocity equation would be 2t minus 1 to the 4th power Now my tablet's going to start freaking out. It's always right near the end of a video. 2t, oh, yep, 1's disappearing. So 2t minus 1 to the 4th plus c. So this is where that initial condition comes in. So 0 is going to go in everywhere. So I would get 2 times 0 is 0, minus 1 to the 4th, plus some unknown value, and that's going to need to equal negative 3. So 0 minus 1 is negative 1, and negative 1 to the 4th is 1. So 1 plus my constant has to equal negative 3, therefore c equals negative 4. So my velocity equation would be 2t minus 1 quantity to the 4th power minus 4. So that's it. That is my velocity equation. So again, we did u-substitution there to help us evaluate that integral. Now we're going to do the same thing to start with this function and go back to the original position. So that's my next step. So this one I'm going to use brackets because I've got this group inside of here. So 2t minus 1 to the 4th minus 4 dt. So for this one, so there are some problems where this happens a lot of times with two terms where one of them would require chain rule, but the other doesn't. So in that case, especially when it's a definite integral, my recommendation is to split it. Okay, we don't want to mix stuff that was in terms of x, or in this case t, and then stuff that's now in terms of u. That's not a good idea to write your integrals that way. So I'm going to make this the integral of just the first term, 2t minus 1 to the 4th dt, and then minus the integral of 4 dt. This guy requires u-substitution. And it's really going to be the exact same setup that we just used. So u is still 2t minus 1, du is still 2 dt, but now in this case, I don't have that 2, so I'm going to multiply by 2 inside, 1/2 outside. This guy is perfectly fine. We don't need to fix anything there because it's just a constant. So when I rewrite this, though, the first one would now become 1/2 times the integral of u to the 4th du. This guy I'm going to leave alone for right now. Now, because I separated it, technically each would get their own plus c when I find the antiderivative. But again, a constant plus another constant is just some other constant. So we don't have to worry about writing them both. We're just going to write a standard plus c value at the very end of all this stuff. So 1/2 we would get times u to the 5th over 5 minus, then this guy will become 4t plus c. And now we can go ahead and replace that u in terms of our t. Once we get outside of the calculus, outside of the integrals, it's not as big of a deal to write stuff with u's and t's in it. We just don't like to do it inside of the integrals because of our du and dt quantities. Technically speaking, those differentials act differently with different variables inside of there. So what this becomes then is 2t minus 1 to the 5th power over 10 minus 4t plus c. So that is my position equation, the general solution to it. And now, just like before, we're going to use our initial position to help us solve for that c value. So let me do that over here. So we get x of 0 would create, up top, we would have 2 times 0 is 0, 0 minus 1 is negative 1, negative 1 to the 5th power is negative 1. So we have negative 1/10 minus 0 plus c, and that is supposed to equal 0. So that means c is equal to 1/10. Not sure what exactly that's supposed to be on top. It's supposed to be a 1. So that is my c value. So my particular solution for the position function is all this stuff over again, but 1/10 is going to be there at the end. So minus 4t plus 1/10. So that is my position function. Make that look a little closer to a 10. All right, now for the next part, now that we have those two equations, now we can kind of use them to do whatever we want. So for part C, now not all of this has to do with, directly with our integrals, but there's multiple ways to do some of these. So for C, I want to find average velocity of the particle from 0 to 1. So there's actually two ways to do this. Now that I have the velocity equation, thanks to part A, remember we have our average value theorem for integration that says anytime that I ask for the average of something, I take 1 over b minus a times the integral from a to b of that quantity. So if I were to integrate v of t dt from 0 to 1, I would get the average velocity. Now the alternate way is average rate of change through the mindset of differentiation. Remember that velocity is the change in position. So for average velocity, we would be taking the position of the particle from x minus 1 to or minus the position of the particle at x of 0 over the time span, so 1 minus 0. So you're going to see we eventually end up with this anyways, because if I set this integral up, we get 1 over b minus a, so that's actually just 1 in front. We can write it, but it's not actually going to change the value of the integral of v of t dt. Well, I can actually do this all with the name of the function because we already have the equation of x of t. We actually don't need to do all that math over again. Because if I do it with the names, then what I end up with is, well, I know the integral or the antiderivative of velocity is position. So we get x of t from 0 to 1. So then we just get x of 1 minus x of 0. Now, the only reason why this doesn't look like the fraction that we had over here is because this 1 over b minus a really is just 1 over 1. So it just ends up being these two values. So to answer this, we know the first, or the x of 0, that is 0. That's the initial position. So we were told that already. So we know this guy is 0. So all we really have to do is take 1 and substitute it into our new position function. So let's do that real quick. So x of 1 would give me 2 times 1 is 1. Excuse me, yikes. 2 times 1 is 2, minus 1 is 1. 1 to the 5th power is 1, so I get 1/10. Minus 4 times 1 is 4, plus 1/10. So I get 2/10 minus 4, or 2 2/10 minus 20/10. Or excuse me, yikes. You can tell it's the end of the day. Minus 40/10 would give us negative 38/10, or negative 3.8. So that goes here, but we're subtracted it from 0, so that really is our final answer. So the average velocity of that particle over that interval is negative 3.8. And again, we don't really have units unless they establish units in the problem, but it would be something like meters per second or inches per second, something like that. Okay. Now for part D, we want to find the total distance traveled by the particle. And again, thinking back to the last video when we looked at the fundamental theorem and our net change stuff. So wherever this particle starts, it can be moving left, right, it can continue to bounce back and forth all you want it to over across any interval. But we end up with two important quantities. Displacement just means what's the difference between the end value and the start value. So displacement would just be this many units away from the beginning. That's where we ended up. We ended up X number of units to the left. Total distance traveled is the length of all these lines that I drew back and forth. The only way that we can calculate that is if we disregard what direction we're moving. And that is where we take the integral from 0 to 2 of the absolute value of our velocity function. Okay, so this one would definitely be a calculator problem. The only way that you could do this by hand is if you know what the graph of the original looks like and where it crosses the x-axis so that we can fold it up. Then we have to break it up into a bunch of integrals. You should have seen a couple of those like that in the 4.5 packet. But for this one, we're just going to use our calculator. So this would be another one where I'm going to take my velocity function and store it into y1. And then I'm going to use, again, older calculators, you're going to actually create this on your screen. We go to math option 9, which is fn int, and then we're going to tell it where the function is, what variable we are integrating with respect to, and then we're going to go from 0 to 2. So when I punch this guy into y1, I'm actually going to put the absolute value bars around it That way I don't have to worry about doing it twice. Again, you also have the option of just putting the regular velocity equation into y1 and then making the absolute value in y2. So let's try this guy here real quick. So I'm going to go to y equals, let me get rid of what's in here right now. Let's go back to our velocity equation. So that would be right here in blue. So I'm going to type that guy in. Now remember, your calculator does not use t, so we're going to use 2x minus 1 to the 4th power. And then minus 4, yep, just minus 4. And I already lied, so I have the regular velocity in y1, so let's actually do it this way. We'll go to math, over to number, absolute value, and I'm just going to tell it to take the absolute value of y1. Remember, I do that with vars, y vars function, y1. So my fn int then, if I exit this, and I do math 9, remember, newer calculators, it'll look like this guy. But now, because I did it that way, I separated them. Now I need to recall y2 for this integral. So option 2, and then dx. Now again, you have the two choices. I just forgot to do it, so that's why we ended up doing it this way. So in this case, the total distance that particle travels over that interval, sometimes it does take a little while for the calculator to think through these integral problems, especially the absolute value ones, because it has to chop it up into pieces. We get 24.725. So that would be our answer here. 24.725. Now, just so that you have something to compare that to, let's do the same thing over again. Not that it asks you to do this. At least I don't think it does. Haven't read to the next part, if there is a next part. But let's just do it with the regular velocity equation. So this would be calculating displacement. So 16.4. So because these aren't the same thing, that means that the particle must have changed directions at some point. So the distance from where we started to where we ended up is not the same thing as the total distance traveled. So that means there must have been some backpedaling or overlap between where we started and where we ended up. Okay, so that's what that means. Anytime that displacement and total distance traveled are not equal, there had to have been a change in directions in there somewhere. And that is it. And yep, there is no part E. So that is it for integration by substitution. Good luck.